India. Before that, he worked at NIT Delhi and Indira Gandhi, then Delhi Technical University, New Delhi. Dr. Prakash is teaching and research experience of over 14 years. He is the founder of the Computational Intelligence in Smart Motion Robotics Research Group. Dr. Prakash received a PhD degree in machine learning from Malviya Institute of Technology, including Jaipur, India, in 2018. Dr. Chandra Prakash is 2010 alumni of the Indian Institute of Information Technology and Management, Gwalior, India. From there, he pursued BTech and MTech in Information Technology. His areas of interest are artificial intelligence, machine learning, motion analysis, reinforcement learning, computational neuroscience, gait analysis in healthcare, biometrics, gait and face recognition, and natural language processing. Dr. Prakash has two patents and authored more than 70 publications in research journals, book chapters, and conferences. Currently, he is the principal investigator of SERB sponsored project. He is a recipient of 6 best papers at different international conferences. He is a recipient of the scholarship as Junior Research Fellow in DST funded project, the Lord of the Code Scholarship from Red Hat and the IIT Bombay. I welcome you, sir. Over to you.
Thank you for the introduction. Let me share my
Welcome,
screen.
Dr.
Please let
Prakash.
me know. Namaskar, ma'am. कैसे हैं आप?
Namaskar.
How are you?
Sab fine hai. All fine, all fine. Welcome.
Okay, thank you. Let me share my screen. Please let me know if it is visible. Is it visible now?
Yes, sir.
Okay. So today I will be talking about the brain-computer interface and how we can use the different machine learning models, especially the sequential model, for the processing of the signal that we acquired from the brain. So before going into the deep, I would like to show you some of the applications of AI. Please identify the medical applications of AI, right? Are you able to hear the sound?
Yes, sir, you are audible, but
Yes, sir, we can hear you.
My screen is also visible, right?
yes, sir, yes, sir, yes, sir.
Okay.
Yes, sir. I am an explorer. Searching for the origins of our universe. And charting a safer path to other worlds. I am a helper, moving us forward one step at a time.
This is the area where I work, gait analysis.
Giving voice to every emotion. I am a healer, modeling the future of medicine. Finding a needle in a haystack. Every second counts. I am a visionary, uncovering masterpieces lost to the ages. And finding new adventures in a galaxy far, far away. I am a builder, driving perfection in everything we create. I am even the narrator of the story you are watching. The story you are watching. and the composer of the music. When the world faces its greatest challenge, and give us the power to take it on together. I am AI.
So what are the applications that you just saw in this video? Medical application. Hello. Am I audible? Hello.
Yes,
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 sir.
you
Yes,
are
sir. Yes,
audible.
sir.
You are audible.
Okay,
They
okay.
don't want to respond you back.
Yes. What are the applications that we just saw in this? You may unmute yourself and then you can speak, or you can type in the chat as well.
Dr. Prakash, I think you can elaborate. I guess they are not able to identify.
Yeah. Okay. Okay. So basically, in this, the motion analytics was there when where a particular person was walking with the help of some uh, exoskeleton, right? The brain computer interface was also there. So today we will be talking about that brain computer interface in detail, and we will be taking the help of the machine learning. So machine learning we can divide into these three parts mainly: supervised, unsupervised, and reinforcement. Today we will be talking about the deep sequential model. So that is part of the supervised learning. So let me again ask you some question. If this is a ball, right? Can I identify in which direction it will move? Come on, you can tell.
Sir, based on we move it, whether it right direction or left or right, can move in any direction based on
Yes, it can move in any
any
direction
direction.
because there is no sequence in it, right?
Yeah, yeah. There is no
It can move
prior
in
information.
any of these, right? Now, if I want to identify in which direction it will move, so for that, what I need to have is the past data. So basically the sequence. So based on this, now easily I can identify that it will move forward
Right.
in the right direction. So this is an example of sequential data. In nature also, we have a lot of this type of the data, right? This is very famous, your heart rate, then the ripple effect in the water, right? We use the sequential model in case of the forecasting of the stock, right? uh, the temperature, even the COVID cases, the music, right? Your brain activity, right? All these are the example of sequence modeling problem. The methods that we will discuss today, it is very much applicable in all these areas, right? So before going into the methods, let us first talk about the brain computer interface, right? So as a human, we have the five senses, and we interact with the world based on these senses only. And whenever we, let's say, touch, right, this fire, instantaneously your hand, right, you pull your hand back. Now, what is the reason? Because the message, uh, right, from the brain, right, it suggests that please pull your hand back. So this signal is there. So the branch of the physiology that deal with the flow of the iron in the biological tissue is the electrophysiology. Under that, we try to record these electrical signals, right? There are different methods. One way is that we can record these electrical signals or the flow of the ions using the EEG based methods that we will discuss today. Another is the electrocardiogram, that is the basically the heart pattern. Based on that, we can identify whether it is a normal or abnormal, right? Or there are there may be some potential risk also in the near future. So to understand these biomedical signals, it is necessary to understand what is the signal and its property. So there are certain few interesting facts about your brain that approximately it weigh around 1.36 kilogram. There are approximately 100 billion of the neurons in your brain, right? And the rate of the development of the or this neurons is approximately 2000 250,000 neuron per minute in a developing fetus, right? And we can store around 2.5 petabytes of the memory or information in our brain. These are some interesting fact. What we are interested in that that how to capture this signal that is moving over here, right? So for that we need to understand that what are the parts of the brain, right? So we divide the brain into three main part. One is the cerebrum, another is the cerebellum, and the third is the brainstem. Now, based on these three, right, because we need to acquire the signals, so we need to see that which particular part of the brain is more active for one particular kind of the activity. So, in case of the cerebral cortex, we divide this whole region into four parts. The first one is this frontal lobe. Then we have the parietal lobe, right, over here, and then the temporal lobe and occipital lobe. Now, why these lobes are important? Because when you will study the brain signals, you need to understand that what is the application that you are interested in. For example, if I want to see whether a particular person is able to sleep in a good way or not, right? So certain reason is active to identify that. So this frontal lobe, it is very much active. This one is very much active in case of the reasoning, thinking, planning, languages, emotion, right? While the temporal lobe over here, it relates to your memory, how you understand a particular language. The parietal lobe is responsible for the senses control over here. It related to your smell, taste, touch, right? Hearing related issues. This occipital lobe, it is related to the vision and color identification. Your brainstem over here relates to the steam, breathing and the temperature, your heart rate. Cerebellum is the one that is responsible for the coordination, balancing, and your attention. So, in case of the brain-computer interface, what we do, we try to get the signal from the brain, right? For that, there are different ways. Either we drill a hole into the brain and then we capture the data. This is known as the invasive based method. Another is that this is not advisable. It is only possible for very severely uh, in case of very severe disease, I will say, if a person is in coma or something like that, right? For most of us, we prefer the non-invasive methods, right? So once we have that data, then we give that to the computer, and based on the computer, we try to control certain particular activity or certain peripheral, right? So BCI deal with the direct communication between your human brain and the external device. So in this, the first step, as I told you, we try to acquire the brain signal, we analyze it, we translate them into some commands, so that my output, these, let's say I want to control a robot or a wheelchair, I can do that. So based on the brain activity, I try to come up with certain control. These are some of the applications, right? Clinical trials, your sleep quality, fatigue, emotion, robot control, game interaction, all these are the application of the brain computer interface, right? With the help of this, we can also type or some numbers and like that, right? So a patient who suffer from severe motor impairments, right, such as ALS or the cerebral palsy or some trauma or spinal injury, over there BCI system has an alternate form of communication by mental activity. Even though it's not easy to acquire or to work on this particular area, because you have to pass lot of you have to take lot of ethical clearance from the doctor and the other agencies. So when we are talking about the signals, right, so signal is a function of one or more independent variable and that contain the information about the behavior of some particular phenomena. There are different type of the signals, right? System usually respond to particular signal by producing another signal also. So signal is a representation in the form of the amplitude versus time. We called it as a waveform. Our brain also exhibit different waveforms. So these are the patterns. So in our brain, as we discussed earlier, that we have multiple neurons, and each neuron, they are connected to another neuron. Same concept. So basically we have this dendrites. These are the dendrites, so which are responsible for passing the message from one particular neuron to the another, and in between them there is this very small gap, right? And this is the reason why we uh, face the threshold whenever we try a new thing, right? So researcher, what they did, they used the concept of this biological neuron, and then they converted it into the artificial neural network. If you are working in the field of the machine learning, deep learning, then you have to work with this ANN. Nowadays, deep learning is also there. Now, how the brain generate the signal? So based on the dendrites over here, right? This is very small gap, this one, right? So what happened? 100 of the billion of the electrical impulses, that is in the form of the action potentials, are transmitted in the body. When the neuron communicate, the current, a very minute amount of the current occurs, right? And an electrical signal is transmitted along this axon over here. This whole is an axon or a dendroid. This is the dendroid. So what happened? Now this small gap is there. So electrical signal at the end of the axon is converted into some chemical signal, and the axon release the chemical messenger. We called it as a neurotransmitter. This neurotransmitter, it travel in this particular gap, right, and it reaches to the dendrites, and again it converted back to the electrical signal. So this is the signal that we are interested in, right? But it produces the electricity at a micro voltage, so it is difficult to acquire, because our brain uh, in that we have the skull, right? So this skull act as a electrical insulator. So we are not able to capture the signals, right? Because of this skull. It is difficult to record from the individual neurons. So big number of the neurons do the same thing. So what we do, the possible to see the activity with the electrode placed on the surface of the skull. So we try to place some electrode over here and then one electrode over here, like electrode over here, and then we try to find the difference. Signal are strong enough to move the robots and the prosthetic limb. But this is the interesting thing that even though our skull, right, act as an insulator, still using non-invasive methods, we can move the robots. So as I told you that there are different ways to implant the electrode. One is the invasive method where we uh, come up with a hole in this skull and then we install a particular chip over there, right? But this is not advisable. The another one is the partial invasive where we instead of going deep, we put a very minute hole as you can see over here, and then we acquire the signal. So this is known as ECOG. While the non-invasive method that we are interested in, we can capture the signals using the EEG based methods, right? This is another same example. So we are interested in this non-invasive methods. Now, if we talk about the brain, and if I cut it in from this particular section, so over here, this is the gray matter. In between, we are having the white matter, right? Now, how to identify the this voltage? So for that, let us again try one particular exercise. All of you must have did this earlier as well. Try to find the difference between input A and input B. Can you tell me how many differences you are able to identify in it? Yes. Okay.
So,
Three.
four differences, sir.
There are.
Four.
Okay. So what we try to do, we try to find the difference over here. So 1, 2, 3, 4, 5, 6, 7 differences.
7, yeah. And input 1 and 2 also different.
Yes. So this is a visual problem, so all of us can do that. Now the question is, if I convert this into a signal, how to identify? So there are different type of the amplifiers. We call that as a differential amplifier that actually amplify the difference between the two input voltage, right, by surpassing any voltage common to the two inputs. So if let's say this is first input, this is second input, so the difference over here is this red one. So using the differential amplifier, we can identify the difference. And we are interested in this. So using the differential amplifier, we can come up with the differences uh, uh, for the given input, right? So as I told you, again, in this non-invasive methods, there are different ways. One is this EEG, which measure the electrical potential differences that we are interested in today's talk. Another is MEG over here, that is it detect the magnetic field. Then we have the fMRI, it measures the hemodynamic responses, particularly magnetic dynamics of the protons. Then we have NIRS, that is the near infrared spectroscopy. Then it actually measure the changes in the intensity of the IR light, and we have this FTCD. We will talk more about the EEG now. So the recorded waveform, it reflect some activity of your brain, right? EEG activity is very small, so we need to see that how to measure the frequencies, right, or the waveforms that we acquire. So we can divide the waveform from the brain into these five parts. Some of the literature, if you are into the BCI area, then they consider four waveform also. Now the interesting thing over here is each particular wave is responsible for one particular task or one particular type of the activity. So this gamma wave, using the gamma wave, we can identify what is your mental state, right? It's higher mental state. If you are in the higher mental state, then gamma waves are more active, right? Motor functions uh, is also a part of it. Then beta waves basically talk about uh, how much you have the concentration, right? Power, focus is there. Then alpha wave, when you are relaxed, then alpha waves are more active. So right, so if you are listening some music, right, one can also identify the role of the different mantras, right, on the brain, right, on your day-to-day activity. So researchers, they try to prove that because of these mantras, your alpha wave actually increases as prominent as compared to other waves. If we want to measure the deep meditation or your creativity, light sleep, then theta waves are observed. And for the person who are not actually able to sleep, the doctor, they see that what are their delta waves, right? So this non-invasive based methods, EEG based, it requires some electrode attached to the scalp with some gel. It requires physical connection to the machine. So we do have different caps with us. There are different type of the channels. Some come up with the 8 channels, 20 channels, 32 channels. Now, once we have that channel with us, we record the signal. This is a common methodology if you will be working with in the BCI. So we have this raw data. Now, the interesting thing and the open research problem is that even when you blink your eye, right, if you hear something, right, then it affects my signal. So when you are acquiring the signal, it should be very, very quiet environment, right? So we have certain setup, lab setup where only that particular person is there, uh, or the subject is there from whom you want to acquire the signal. And then you remove the artifacts after applying different signal processing methods. You extract the features. Then after applying the algorithms, machine learning algorithms, you come up with certain event related potentials. Once you identify that, then you can easily send it to the end devices, right? You can control your robot, you can control your wheel or some particular hardware. So how we acquire the signals? So for that, uh, your this nose part is the nasal, and is your back of your hand, right? So over here, uh, this is how we actually put the skull, right? So we have different standards. One of the renowned standard is 1020 system. This 1020 system is the system that actually help us to acquire the signal from different parts of the brain. So it is known as 1020 because we divide our whole this region from this area to this particular node into 10, 20, 20, 20 and 10. Then Same thing, we also divide from one particular year to the another year in the same aspect of 10, 20, 20, and 10. Then from here we take 10 percentage, right? This is the 25 percentage, and correspondingly we come up with these type of the configuration. So your channels, they acquire the signal from these particular regions, and these are we have given them some names. F represent the frontal part, so this is basically the frontal lobe part. C represent the central part, so this is the central part. And your P, it represent the parietal. So from that we try to acquire the signal. Now this signal, these different positions we have identified. Once we identify these, we associate some number with it. As you can see over here, even number on the right and odd number to the left. Lower number is more close to this midline, right? As in the case of the left and the right, as you can see, Z represent the 0 over here. Now, these signals we acquire using the concept of the montage. So from the individual discharge directed by the electrode, EEG give rise to a rich set of the data across the entire span of the scalp, and we do that using the montage. Montage means the placement of the electrode basically. So there are two broad categories of placing the electrode. One is the bipolar and another is the referential. So in referential, again, we have this common reference and the average. Now, what is the meaning of it? In case of the bipolar montage, what happened that one particular electrode over here, and we try to find the difference from the another one. So we call this as FP2 F8 channel. Likewise, we have more other channels. So in a bipolar montage, each electrode voltage is linked to compared to the adjacent one. Then we can have similarly F8 and T8, T8 and P8, right? Same case FP1 and F7, as you can see over here. So if you will be working with the brain computer interface or EEG signals, then you will be having the data in this format. So now you can understand actually what is the meaning of these signals, right? In each chain, an electrode voltage is compared to that of the electrode just behind it. If the first electrode in the tracing line is more positive, now you can see over here, this is higher, this is lower. Now, what is the meaning of it? So if the first electrode, let's say this one, and this is the second, this is the first electrode. So if the first electrode in that tracing line is more positive or higher than the second, you get a positive downward deflection, this one. If the second electrode is more positive or higher, you get a negative upward deflection. So as you can see over here, I am having signal as minus 5 microvolt over here, where F8 I am having minus 20. So if I subtract it, it came out to be 18. So it is downward, right? If minus 20 and 40, so plus 20. So again, it's positive. Same case over here, it's negative, so it goes up. So this is the meaning of ups and downs in case of my montage based EEG signals in case of the bipolar montage. Now, beside this, you can see, let's say I am having these different signals that I acquired. So this is for the left temporal, this is for the right temporal, right? This is for the left parasagittal chain, right? So in this way, we have these different signals. If you are working with the motor imagery related signals, then in that case, there are different studies that suggest that we get more uh, informed signal from this particular area. So this is the signal channel based. So there are certain common reference motors, right? So not look the difference between the adjacent electrode, but in case of the reference montage, what we did, we identify the difference between this electrode with the zeroth one, CZ. So this is the reference montage. Commonly, there are different ways, difference between the electrode of the interest and the average of the signal of the rest of the head. Laplacian montage is also there. So as you can see over here, we come up with the different type of the montage. So if this is a signal, then we have these different channels with us. Now we have the brain wave signals. Now what we need to do, we need to analyze it. So using some of the machine learning methods, we try to do that. So let us see what are the methods that we can apply on these brain waves. So sequential modeling, as we discussed earlier, right? So if this is my input, this is my output, right? So this is one-to-one. So binary classifications are can be used over here. We cannot use this uh, in the sequence modeling. So this is an example of the neural network. Another may be that if I am having multiple input, right? And then we can come up with a output. So these are the different ways, many to many, we use it in the case of the sentiment classification. Our image is there, and then we can have come up with the multiple captions of it in various languages. Then again, we do have this one to many. We have also the sequence modeling in the form of many to many, where I am having a sequence in a particular language and then I convert it into another language. So for that, we can use the concept of the perceptron or the neuron that we discussed earlier, that we were having different data corresponding with, we have certain weights associated with it. So over here, we sum all these weights, and then after that we apply the activation function using the artificial neuron concept. So we can propagate the signal forward in this way from the input to the actual output. So this is how we can send the signal using the feed forward network. So now what happened? How the question is how to handle the sequence or sequential data. So I'm having a data as x0. So correspondingly, I'm having a data as y0. Then at next instance, I am having x1. Then corresponding data output is y1, x2, y2, likewise. So this we can combine all these together, right? So where we can say that my predicted output is a function of input, right? So we can also say, because it is in the sequence, so whatever the output over here, it also affect the next one. Whatever the processing over here, it affect the next one, because my brain signals are continuous signals. So we can write it as that my output of yt hat is equal to a function of the input, that is the xt, and some output, we call it as a ht minus 1. So this xt is my input and this ht minus 1 is my past memory. and we combine this whole together, this sequence, right? It goes till n, x, n. So we can convert them into a recurrent neural network. We call, because over here, this cell, right, we are sending the data again to it, right? Of course, the time duration will differ. So input to output mapping can be thought of as a recurrent neural network for the sequential data. So this RNN has a state HT that is updated at each timestamp as a sequence it process. Okay. So we apply our recurrence relation at every timestamp to produce a sequence, right? So mathematically, how we can represent it, my cell state HT is equal to a function of my old state, that is the HT minus 1 into the output over here. Sorry, this output is my xt hat. So this same function and set of the parameter are used at every time step. So I need not to give the whole data again as if I will be using a simple neural network. So how we update the state, my HT, in that we apply an activation function as 10h, where it is the combination of the weight of the previous instance into the HT plus weight from this input. So over here, this is my WXH. And over here, this is my WHH. This weight on this and this weight over here.
Excuse me, sir.
Yes.
So here the time which we are taking, does it have any consideration like if you have different values of time, will it give the different results?
Yes, of course it will, because your association changes in that. Right now, I'm considering that you are having a sequential data, right?
Right.
Okay.
Okay. Thank
So
you.
we can use this in the form of the graph. We can reuse the same weight matrix at every time step. It is similar to the CNN, and thus it reduce the number of the parameter we need to optimize. And it allow us to process the arbitrary temporal size of the input. So my RNN actually is the representation of the sequential data across the time in this way. Sorry. So in the neural network, as we have the concept of the forward pass, similar to that, what I will do at x0, right? I will be having this y0. At x1, I will be having y1. At x2, I will be having y2. Now, at each particular timestamp, I do have the actual output also, right? So my, let's say, actual output is y0, over here y1, y2, yt. So we identify the difference, or loss, or we call it as a loss over here. So my loss at L0 is nothing but it may be the under root, it may be the absolute value of y naught minus y naught hat. My actual minus my desired output. Same case over here. So we can combine all these loss as capital L, and then we need to back propagate it also, right? So in case of the vanilla neural network, that is one-to-one, as we discussed, we cannot use this as such for the sequential modeling. So we have to come up with some other type of the uh, representation. So this is one-to-one, this is one-to-many, many-to-many. Already we discussed this. So over here, to handle the variable length sequence, we track the long-term dependency also. We use the RNN over here. So let's say a particular text is given to me, and I need, based on this text, I want to predict the next one. Right? If so, this is I'm taking example from the natural language processing (NLP). So we cannot use the vanilla neural network as such, right? Instead, what we need to have some association of these terms, some embedding, right? So this is embedding. Then we give it to the network, and then correspondingly we can get the output. Again, it will be in the form of some uh, probability, of course. So embedding is transform indexes into the vector of some fixed size, as I told you, right? So from my vocabulary, let's say I am having these words. These are the corpus of the words that I am having. Along with these, I will first index these words, and then after that, for every particular index, I will associate one hot encoding, and then we can plot this in a multi-dimensional environment, right? So for in that environment, we can identify that, okay, this run is similar to walk, dog and cat are similar, right? Of course, we need to convert these into some particular numbers. So for that, we are using the concept of embedding. This embedding is the base of the LLM models that we use today. Yeah, even your chat GPT is also based on using the concept of the transformer. In transformer, we are using the concept of the embedding. So we have talked about the forward passing. Now the back propagation through time, BPTT, is also there. So once we propagate our information, then we need to update the weight. So for that, we are using the back propagation, right? We shift the parameters so that we minimize the error. So we discussed that in the forward pass, we come up with a L value, overall loss. Now what I need to do, I need to propagate this loss back, right? Same case over here in this way, so that it update the values or with the weights, and correspondingly it come up with the optimal weights for that particular problem area. So there are different methods. This is the standard RNN gradient flow. Now what happened over here, because it is a very large sequence, so because of that we encountered these two problems. One is known as the vanishing gradient, another is known as the exploding gradient. In case of the vanishing gradient, what happened, that let's say if my value is very small, right, and because it has to pass to n number of the sequences and number of the states, so it will reduce to very small number, because at the end we are multiplying these values. So as you can see that if I'm taking an example of 0.1, then if I keep on multiplying it, right, so it is a very small number that at the end I will be having. Another problem is that if this value is very
Hello.
high, then
Professor?
we have
Sir, I have a doubt. Hello. Hello, Professor.
yes.
I have a small doubt. If you are writing lot of machine learning algorithms, once you give basic algorithm into the AI, means it will create and give these outputs. Why we need to again and again repeat yourself to do like this? If AI do means easily fulfill this type of algorithm, it's possible or not?
Come again. What's your question is?
So nowadays you are giving lot of algorithms in your PPT. I'm asking if one basic algorithm we give into the AI, artificial intelligence, machine learning, they will create and give the solution for this one. It's possible.
Uh, Let me ask you one question. Can you do all the jobs in this world? No. That's why, because if I am good in, let's say, teaching, so I do that work. Same case, we are having multiple models. They are used for some specific set of the problem set. We cannot say that a particular problem is there. It is applicable for the vision based. It is applicable for the signals. Again, in signals, there are multiple limitations also. So for that, we are having multiple technologies, right, or models. So I'm talking about three basic models today. One is the neural network, then RNN, and last is the LST.
This RNN and neural network is already available algorithms. So that's why I'm asking if we give this algorithm to the artificial intelligence means they give a lot of possible outcome of the particular RNN and CNN network. It is possible.
Uh, I am not aware you have gone through the RNN or CNN. So I am talking about these models.
Yes, I watched all your PPTs till now. I'm your slide. That's why I'm
Okay.
asking. Okay, boss.
At the
Okay,
end, if you have any specific question, then we can discuss. Right.
okay, thank you.
Okay. So this RNN is used for the time sequence based problems. The another one is that we are having this exploding gradient, right? So now, in case of the exploding gradient, the gradient clips to the scale big gradient. So what we can do is that now we need to see that how to overcome this particular problem. So for that, we again come up with another algorithm. We called it as LSTM, right? So in this, the issue, let's say I am having a very small sequence. I'm taking this, borrowing this particular example from the NLP. So try to understand it, that a sentence is there, in only one sentence is there, right? So the dependency of the this particular word over here is based on these five only. But if I am having a very long sentence, right? I grew up in a France and I speak fluent. So what I need to write over here, it depends on the first few lines. So that long dependency we need to see. So, and along with that, we have the vanishing gradient problem. So there are different methods. One is that I can change the activation function, right? So earlier we were using the sigmoid and 10H. So I'm using the ReLU. Now, another method is that I can initialize the parameter in such a way so that it helps the weight from sinking to zero. The third method is the gated based cells. We call it as a LSTM network. So this LSTM play an important role. And nowadays we have one more advanced, we call it as an attention network. Right? I'm not talking about the attention in this particular discussion. Right. So this LSTM, it reply or based on certain gates, right? In a standard recurrent neural network, right, we have this type of the gate. This is known as the standard vanilla RNN also. So in case of the LSTM, that is the long short term memory, right, where we try to have both the concept of the short term memory as well as the long term memory. So the information that we need to keep, right, for long period. So over here, this short-term dependencies are there, as well as the long-term dependencies may be there. Long-term dependency help us to work with the area where or the problem where we are having a very large sequence, right? So based on these gates, we are having these three states. One state, it decide what to forget, another decide what to remember, third decide what should be the output. So in case of the LSTM, we call it as a gate, as I told you. These three gates are there: forget, store. Over here, this part is store plus update, and this is the output. So in LSTM, the forget irrelevant part of the previous state. It is similar to how we remember few things, right? If I want to forget, then I do some yoga and other thing. So similar to that, we have a gate over here. We called it as a forget gate. Then this LSTM, it selectively update the cell. Then we have this output gate to output certain part of the cell states. Over here, you can see we are using the sigmoid again. So in case of the forget gate, right, we have this sigmoid. It is similar to your previous simple neural network, where we do have the sigmoid based on some particular input. We after that we apply the. So in case of the neuron, what we do if we are having different inputs, so we first sum and then we apply the activation function on it, right? So this activation function is same. So it is similar to your simple neuron. Then in the second, in this update gate, right, we decide what value to update, because everything we should not forward, right? So over there we apply this sigmoid, in that we apply this IT also. And here we are applying this 10H sigmoid, 10H activation function. It generates a new vector of the candidate value that could be added to the state. So we are updating also. Then we add the information that we get from the first particular cell. Then the third one is the output gate. So in this, we are using the sigmoid layer again. You can see it decide what part of the state to output. Then we are using the 10H, right? So that what the values, it lie between -1 to 1. So in case of the LSTM, right, the back propagation is also possible, so that it require only the element wise multiplication. No matrix multiplication is required, and because of that we avoid the vanishing gradient problem. As you can see over here, uninterrupted gradient flow is there. So in case of the LSTM, we maintain a separate cell state from which it is output. We have the forget gate, we have the store gate and update, and then we have the output gate also. Now using this, we can come up with the different models, right? You can come up with the deep RNN models. You can come up with the bidirectional RNN models. And let us talk about how we applied it on our own data, right? In that, we did a small study on the MOOC courses based signal from the brain. In that, we try to identify that whether my student, they are able to understand uh, the lecture or not, right? So there is one concept of the brain fog, where which is also known as the confusion. In technical term, it is known as the brain fog. It is one of the main reasons for the low performance in the learning process or any kind of the daily task that involves and required thinking. Right? If I am taking an online class, right? Nowadays there are a lot of online courses as well. So based on the feedback, we can identify that yes, what are the uh, total outcome of this particular course. So we worked on a publicly available EEG brainwave data of 10 students watching these different MOOC video clips. In this, we assume that the college students, they will see that particular video online, and we are acquiring the signal. Basically, that particular data set, they acquire the signal using the cap, and then certain different type of the videos were shown to the student. Some related to the basic algebra and the geometry, where students is not familiar with the video topics like quantum mechanisms, stem cell research, or brain computer interface, like that. Then prepare 20 videos, 10 in each category. Video was about 2 minutes long, divided into multiple clips, as you can see over here. Then the user need to give a uh, level, a scale of from 1 to 7, confused, non-confused, right? So what we did, as soon as we get this data, the first thing we need to do is we should plot it. We should see that is there any relation between the different features that we are having over here. So in this, we are having the delta, theta, alpha 1, alpha 2, all these wave signals are there, gamma, gamma 1, gamma 2. And then we identify that there is no direct relationship between the feature and the target value. Then we apply the bidirectional LSTM. Uh, in that, we are using the different layers. So this is the architecture that we used. Uh, Over here, total number of the parameters was around 1871233. And then the output accuracy was around 0.7366. For the bidirectional LSTM, it was around 75 in our case. We also applied the deep convolution network. So over here, you can see we applied the convolution. It was 64.0. Now, there are different methods actually through which we can extract this signal, and then after applying the different pre-processing methods on it, it can be converted into some form of the signals, right? If you want to apply the CNN on it, we have to convert it into some form of the images, so that we can feed it directly to the CNN. We are exploring now how we can use the different other models, uh, such as the CME's network, so that it can easily identify. So the major challenge in the BCI are the artifacts, that how to monitor the EEG, because even a small movement, as we discussed, or eye movement, or right, even the cable movements, it affect a lot. There are certain challenges with respect to the hardware and the software regarding EEG. The sensors still have the acquisition limit. We are not able to acquire uh, good quality of the signals. The best signal is the one acquired through invasive technology. So and we avoid that. The other major challenges, if you are working with the BCI, is the ethical issues, right? You have to take the informed consent. You have to see that what are the risks and the benefits in it. Privacy is the another issue. Legal implications are the another issue. At SVNIT, we also have one group on the computational intelligent and smart motion research, where we try to work on the different methods, such as we try to see that how, based on the walking, we can come up with some output, so that we, based just by looking at the video, we can identify that uh, is that particular person is suffering from some disease or not. We generate, when we walk, we generate some signals, right? The use of this, we are planning that using the brain computer interface, we come up with some hardware so that if you think that move left or right, correspondingly that particular exoskeleton will help you to move in that particular direction. We also try to work on the different robots so that we can control using the vision-based methods, right? So, or using the brain-computer interface also, that I can move my hands or fingers. What My scholars are also working on the brain-computer interface. We acquire these signals. So the takeaway of this particular talk is that CNN are well suited for the sequence modeling task. Right, we need to see that can we apply some other methods, because the major issue, because still this is the area where uh, there is a lot of scope, right? If you talk about the image related task, right, almost that particular field saturates, because people are getting 99.9% accuracy also in some of the particular applications. In case of the BCI, it's a new area, right? So you need to see that what are the other methods that we can use, right? As I told you that the new era, where just by sitting at a particular place, you will be able to control the hardware. So people are exploring these different methods. So
What if you could
we
type
start with an
directly from your brain?
video. Let me also end with an
It
video.
sounds impossible, but it's closer than you may realize. The woman
Facebook
in
is
this
actually
video has
working on this.
ALS. She is completely trapped inside her body. She cannot move or speak, but she is typing with her mind, not with eye blanks, with her mind. An array of electrodes the size of a pea has been implanted where her brain would normally control her motor functions.
This
The
is invasive method.
electrodes record her neurons firing when she imagines moving the cursor. Then the computer learns to move it for her. Using this system, she can type 8 words per minute. So what if instead of using imagined arm movements, we could decode speech directly? Now, to be clear, we are not talking about decoding your random.
Right, so this is the future where people are also working. These are some of the references. I'm open for the collaboration. You can be part of the CSMR as a PhD student or an intern. So if you have any doubt, please ask.
Hello,
Yes, I'm open for the questions now.
am I audible?
Yes, yes, you are audible.
See, what can be the ideal state to minimize the variation in the signals for EEG? Let's say we're taking some kind of data set for some certain prospect. So, what can be the ideal state for the subjects to sit or to relax, to minimize the number of artifacts that we get during the recording?
Are you collecting your own data, or you are working on somebody else's data?
So I am also working on the open source data, but I am open to collect the data set.
Yes, for that, as I told you, that it should be a closed environment, right? So if you want to establish a lab for the brain computer interface related thing to acquire the EEG signals, what you need to do is that it should be zero noise room, right? So especially we have to design that type of the room, and even you should not be there while you acquire the signal.
Okay, sir. Also, sir, what according to you could be the best classification model? As I saw in the presentation that you did use many classification models to identify the results. So, what according to your findings, what can be the best classification models to apply on such a data set?
I will say that instead of the classification, first we should work with the artifacts removal pre-processing methods. If you are able to do that, then you can apply the sequential models over here. We are exploring the latest one, the transformers now on these signals.
Right. Thank you so much, sir.
Okay.
Hello, sir. Am I audible?
Yes, yes. you're audible.
Yeah, we have like EEG signals from multiple channels, right? We are collecting the signals from multiple electrodes. So my question is, if we want to feed these EEG signals to a recurrent neural network, so how we are going to feed this?
You are getting these different channels, right?
Yeah.
So what you can do is that you can analyze, you can select one particular channel, then try it. There are two methods now. One is that you extract the feature from that particular channel and then you give that particular feature to your model. Another is that you combine all the signals all together, right? Convert it in some form of the representation so that directly it can be fed to the LSTM models.
Oh, okay. Yeah. Thank you.
Good evening, sir.
Good evening.
Hello. Yeah, sir. I'm working on diabetic retinopathy with the help of retinal images. And like as per my literature review, I got to know like people have worked on CNN model, right? So my question is like if I add on GLCM method for feature extraction along with CNN method, will it give me better results?
We also tried this for the diabetic foot ulcer thermography images. Yes, it did because that
Okay.
act as a good pre-processing method.
Okay. Okay. Thank you, sir.
Okay. Any other question?
Part- Participants, do we have more questions?
Good evening, sir.
Yes, good evening.
Yeah, sir, I just want to ask what parameters we should consider to make the system more generalized, BCI system.
More generalized, what do you mean by that?
That one system can be fit to the different number of the patients or the users to use some application.
No, in BCI there are a lot of scope. Right, we are not in that position. We have not acquired that particular position as we have acquired in case of the CNN based models. Still, we are struggling to acquire the signal, right, in a good way. And then once we acquire the signal, still we are not able to get the noise free signal. So still there is no generalized model over here. So there are a lot of scope as a researcher.
Thank you, sir.
Okay.
Thank you so much, sir, for delivering such an engaging and insightful talk on BCI EEG and not such non-invasive techniques. Their applications, neural networks, RNNs. Your expertise and clear explanations made these complex topics visible and inspiring. Your discussion has broadened my understanding of these cutting-edge technologies and their potential in real world. I truly appreciate your time and effort. Thank you, sir. We do look forward to learning more from you in the future.
Thank you. Thank you for the invitation.
Madam, shall we leave?
Sir, shall we leave, sir? Sir, your presentation is very nice, sir. Thank you for your presentation. I have here.
அப்ப கடைக்கு போயிட்டு வரணும். இந்த அம்மா கண்ட வலிக்கிறது
Participants
ஒரே சோறு தரீங்க. எல்லா பிள்ளைகளும் எப்படி சாப்பிடுறாங்க? சாம்பார் கொடுத்துடுங்க.